hydrogen each.
Carbon
plus
plus
2.
It's double plus 2, bingo. So the way we write that is the generic form is CnH2n plus 2. And one of the ways you can think about that is all the carbons that are in the middle of a carbon chain have 2 hydrogens, right? But the carbons that are at the end of the carbon chain each get 1 extra.
Right.
So that's where the plus 2 comes from. So if we have this ratio, this is the most possible hydrogens that you can have
Right.
for a given number of carbons. And so we call that saturated.
And this is only if you have the sigma bonds, right?
This is if you're only sigma bonds. And no rings. If you have any rings, that's not true either. So if we had C5H10, that actually tells us, that formula right there tells us what types of isomers are possible, right? Because we're missing a pair of hydrogens.
Right.
If we're missing a pair of hydrogens, we have at least 1 ring or pi bond, because a pi bond will do the same thing. You're basically taking away, we'll keep drawing it the same way as the house. If we're giving all of our carbons 4 bonds like we're supposed to, by adding a pi bond between 2 carbons, that also is taking away 1 hydrogen from each of those 2 carbons. So that has the same net effect. So this is going to be C5H10, just like the actual ring structure would also be C5H10. So anytime you're missing a pair of hydrogen, we're always going to see it in pairs. But anytime you're missing a pair of hydrogens, that tells you for every pair of hydrogens you're missing, you've got at least 1 ring or pi bond. Which is one of the reasons why benzene's formula was so confusing at first, because how many pairs of hydrogens are missing? If it's got 6, yeah, it's got 8 hydrogens missing. If it was saturated, it'd be C6H14, right? 2n plus 2. So it's missing 8 hydrogens or 4 pairs of hydrogens. So with only 6 carbons, we've got 4 pi bonds or 3 pi bonds or in a ring, or 2 rings and 2 pi bonds. There's not that many ways you could actually arrange it that make any sort of sense. And they figured that out just based on this initially, just by looking at what we call the degree of unsaturation. The degree of unsaturation is just what we just said. It's how many pairs are missing. So it's not super critical to always think in terms of degree of unsaturation, but it can save you a lot of time in terms of these draw all the possible isomers. Because if you know it's saturated, you don't even need to worry about pi bonds or rings. That limits what possibilities you have. If it was C4H8, all of a sudden that changes how we can arrange things. And I will also say, as soon as nitrogen gets involved, that throws everything off because nitrogen has an odd number of bonds when it's neutral. So we're not dealing in pairs as much anymore because the nitrogen throws off the count. Oxygens are a little bit different too, but we'll get to those in a second. Because today we're mostly focusing on hydrocarbons. And so hydrocarbons, you've probably heard the term before, but it's exactly what it sounds like. A hydrocarbon is made up of entirely of hydrogen and carbon. So no oxygens, no nitrogens, no sulfur, no anything else, no chlorines. And more specifically, so there's, as you can see from this example here, these are all hydrocarbons. Because all of them only have carbons and hydrogens, but some of them have different functional groups. The ethylene, which we'll name when we get to alkenes, ethylene's the common name for it, shows up all the time actually in grocery stores of all places, because ethylene is actually a plant hormone. Ethylene is actually one of the molecules that's responsible for causing the ripening of fruit. So so what they do to ship fruit, especially delicate fruit like peaches and tomatoes and stuff like that, when you ship those to the supermarket, you don't really want them to be in their full ripe state because then they bruise really easily, right? So they'll actually ship them when they're slightly underripe. And then they actually just have small tanks of ethylene that they base in the trucks or sometimes in the back of the grocery store, that they'll basically just like spray this gas over them. It's totally harmless to humans, but it causes the ripening of the fruit to start. So if you've ever heard of if your avocados aren't ripe, you should put them into a paper bag with bananas. Have you ever heard that trick?
No, we put them in the fridge if they're getting too ripe.
Because that slows down the ripening process. But if they're not ripe enough, you can put them in a paper bag with bananas, because bananas famously produce a lot of ethylene.
You put it in a fruit bowl and the fruit bowl normally has bananas in it.
There
That's
you
true,
go.
yeah,
They'll ripen faster that way. If you put them in a paper bag and just like crinkle the top,
yeah. So
then
then it
they'll
like
ripen in like 15 minutes. Or at least soft enough that you can use them.
That's crazy.
And that's the opposite is true sometimes too. You said when they start getting too ripe, you put them in the fridge. You ever heard the phrase, don't let one bad apple ruin the whole bunch?
Yeah.
That actually happens because apples, when they're in contact with other apples, they will actually pass along ethylene and some other compounds to the other apples touching them. And so if one apple is rotten in the middle, you can actually spoil an entire barrel of apples. But if you don't remove it, so that saying's not to say ignore somebody who's being a jerk. It's saying remove them from the situation or it's gonna spoil everything. There was one other, along with the nutrition side of ethylene. I also forgot to mention that saturated and unsaturated, it's the same use of the word that you see for fats. Saturated fats means that there's no double bonds in them, in the fatty acid chains. And unsaturated fats have a double bond in the middle.
It causes the kink, right?
Right, exactly.
Yeah, because then they're like shaped like that, and then that's why like butter is like a solid, whereas like
There you go.
olive oil is a liquid. We learned this in biology, come on now.
So they'd be longer than this normally, but if you look at the bond angles that you get here, so these would all be tetrahedral, right? And they can all freely rotate. If you put for one thing in nature, the bonds of a fatty acid, of an unsaturated fatty acid, they're always gonna be cis. So, you ever heard of trans fats?
Yeah.
They're awful for you, right? They don't occur in nature, so your body doesn't have the enzymes necessary to break them down.
Which ones are those?
They're the ones that look like this.
Real life examples.
They're outlawed in the US as of like 2000. But basically, McDonald's used trans fats to fry their French fries in for a long time in the 80s and 90s because it tasted delicious. And it had less calories if you're using trans fats compared to regular fats, because there's fewer carbon hydrogen bonds. But the problem is because your body can't break down trans fats, they would get incorporated into your fatty acid chains in your fatty tissue. And then they would stay there forever. Your body has no way of breaking them down, so they just sit there. You can't use them as energy, they're just now part of your body forever. So that's why they got outlawed, is because that's not okay.
So it's like a forever chemical, but like for your body.
Yeah, exactly. They're not a forever chemical in nature because they'll burn, they'll break down lots of different ways. But in your body, you can't do anything about it. And so the way that unsaturated fats work, and and then that would continue on. They look like this.
Your body can break that down.
Your body can break that down. And in addition, because it's kinked like that, you can't pack them in as tightly, and they actually have a higher melting point. So that's why olive oil is a liquid at room temperature, but butter, which is saturated, is not. And the saturated fats also tend to accumulate in your bloodstream more. You have more problems with heart problems if you have a diet rich in saturated fats. Unsaturated fats are something that your body needs because it tries to make all of its cell membranes out of these, not those, because you don't want your cell membranes to solidify.
So more olive oil, less butter?
More olive oil, more fish. And you will do better. The other term that gets used is if you've heard of omega-3s and omega-6s, et cetera, that's actually where your body will naturally, or where lots of organisms will naturally put the double bond. Omega refers to the end of the chain. So an omega-3 fatty acid would have, so omega -1, omega -2, it would be right here.
Is where the double bond.
Where the double bond would be if it was an omega-3 fatty acid. And your body can't make those on its own, but it needs them.
And that's like what's in like the fish oil pill.
That's what's in fish. It's oily white fish, specifically.
Yummy.
It is. It's actually really interesting if you go into like the cultural anthropology of worldwide and look at latitude of cultures versus the amount of oily white fish that they eat in their diet. It tracks it's a super strong correlation because the more time you spend inside and the less sunlight you get, the more you need those omega-3s and omega-6s in your diet. Because vitamin D can actually be turned into some of those. And so you can actually track it really well. Part of the reason that you need the omega-3s and the omega-6s is to make vitamin D if you're not getting enough sunlight.
That's
So
crazy.
it's all of these cultures all learned that on their own over thousands of years as they migrated from the equator north or south. But there's a very strong correlation between latitude and the amount of oily white fish groups eat.
Nutrition class.
I taught a nutrition class. I've never taken one though.
I wish like that's the sort of stuff that they taught in a
No,
nutrition
it-
class.
Like I need a
That's
science-based
like
nutrition
so
class.
much cooler.
It was actually a really interesting class, except that none of the students knew what it was supposed to be because the name of the class was like health, nutrition, and sustainability. And so half the class wanted it to be a class on sustainable agriculture and half the class wanted it to be nutrition. And so I couldn't make anybody happy
And you were
because,
History.
and I was just, yeah, exactly.
Chemistry nutrition.
So if you actually go in to take more higher level dietetics classes, you actually do get a lot more of that. Most of the nutrition classes are actually taught by a biochemistry professor for that reason.
So cool.
Yeah, it is. I think it's very cool too. Let's talk about naming things.
Okay.
Used to be compounds just got named randomly. Whoever discovered a new compound would get to name it, and so they would name it however they wanted. Formic acid was first isolated from ants because instead of blood, insects don't have a circulatory system. So inside their body cavities, ants have formic acid instead of like hemoglobin or anything like that. So the first time they isolated formic acid, it was from crushed up ants. They basically like made ant tea.
Oh.
And so they named it after the Latin word for ant, formica. Urea, they first isolated from urine. Morphine, they named it after the Greek god of dreams, Morpheus, because it puts you to sleep. Barbiturates, the first barbiturate is barbituric acid. And this guy who named this compound in honor of a woman named Barbara.
Aw.
Interestingly enough, his wife was not named Barbara.
Oh.
So we don't know a whole lot about Barbara other than probably caused some friction at home. So obviously this is not a great way to name things if you actually want to be, this just means you have to memorize everything. So to
Right.
get away from memorizing things, we instituted the IUPAC nomenclature, which is underneath there, which stands for International Union of Practical and Applied Chemists. So they're the international body that's responsible for naming everything. And maintaining standards and so the IUPAC basically said, well, let's try to standardize this naming conventions. They're also the ones that vote on what to name new elements. Anytime a new element is discovered, the group that discovers it submits their evidence to the IUPAC. IUPAC looks at their evidence and says, yeah, that's good enough, or no, you didn't really make a new compound or a new element. And then the group that discovers it submits their choice for what the name of the new element should be to the IUPAC, and then the IUPAC votes on it.
So you said International Union of.
Practical and applied chemists, I believe. It's also based in, no, that's gotta be right. Fairly certain. Anyway, IUPAC is its own name. You don't even need to know what it stands for, because if you say IUPAC to a chemist or anybody in the sciences, they'll know what you're talking about.
So people have made elements and then these guys have been like, actually, no.
Basically, yeah, because a lot of times the way that they make new elements is in particle accelerators. Basically, you say, okay, I'm going to take a nucleus of calcium 40 and I'm going to accelerate it to 90% the speed of light, and I'm going to smash it into an iodine nucleus. And if you can hit them, yeah, and sometimes that hit them hard enough, you get the two nuclei to fuse and you make a new element out of it. So sometimes, but a lot of times what you wind up making is not stable. It doesn't have the right ratio of neutrons to protons, or it's just too big, and so it immediately falls apart. So IUPAC has some like criteria. You have to have evidence that it existed for longer than 50 nanoseconds or whatever it is. It's a really small amount because some of these are really unstable. But they have like a rubric. And if you think you made a new element, but you don't meet the criteria of the rubric, they say, try again.
Yeah, I remember some of the elements when we first got them like being blank, like they're still finding these.
Let's see, the most recent ones that since I started teaching, they added nihonium, muscovium, tennessine, and ogainsan.
How did we know there were only 118 though? Because I remember like these ones being blank and they're like, yeah, we're finding them, but we know there's that many. And I'm like, how do you know there's that many if you haven't found them yet?
We know that there's actually more than that. You can keep going. But 7 is a really convenient number of rows to have there. When they find element 119, then everybody's gonna have to reprint all their periodic tables.
Is it gonna be here? Is it gonna be?
Should be there. We can say where, and that's why before in the old periodic tables, they had placeholder names, like octium,
Yeah.
that just means 118. That was basically to say, well, we haven't found the recipe for this one yet, but we know it's gonna be there.
So then where does 120 go? Or
So-
what, 121?
So basically, we'll just add another row.
Right, we have one here, but then does it go here or does it go here?
Well, we don't quite know yet. So that's one of the reasons why we need to find it is and try and hopefully. There should be like so a lot of these like 118 and 117 are really, really unstable. There should be a couple of elements in the 120 to 125 range that are actually stable enough that should have half-lives that you can measure in years. Based on the theoretical physics and looking at strong and weak nuclear force and stuff. The physicists have predicted that there should be some pretty stable ones.
Yeah.
And so if we actually find those, they're actually so hard to make that they don't occur in nature, not just in our solar system, but theory, any solar system, because a supernova does not produce enough energy
Oh,
to produce those.
but we think we could make them.
Because we're doing it in smaller amounts. Supernova is a
Okay.
ton of energy, but it's also a ton of mass. If we
Yeah.
take a similar amount of energy and focus it in smaller mass, we could make it synthetically.
Right.
When do we say we found them all?
In all likelihood, never. There's always going to be one more out there. There's not a theoretical maximum for how many we could make. And this is why we keep building bigger and bigger particle accelerators. They thought they built a big enough one in Stanford in the 70s, and then they opened up CERN in Switzerland in the 2000s. They just keep making bigger and better ones, upgrading things like that because we keep finding new reasons to look for stuff. So, very cool. All stuff I like talking about clearly, so I don't mind that we got off topic a little bit. So when we're naming alkanes though, we're still with the alkanes, just looking at, oh no, did we do it again? Okay, no. We're gonna name our hydrocarbons, specifically our saturated hydrocarbons, by finding the longest continuous carbon chain. And that just means if you're taking continuous steps, you start at one end and you just count how many steps you can take until you get to another end of the carbon chain. So for instance, if we just had C4H10, we had two possible isomers we came up with, right? They're not the same compound though, because they have a different longest continuous carbon chain. Our longest continuous carbon chain for the one on the left, 1, 2, 3, 4. Our longest continuous carbon chain here is not 4, even though there's 4 carbons. It's 3 because you're at the end, you went from one end of the chain to the other. And even if we counted the other direction, it's still 3. Right, so we always want to choose which direction we're counting based on which direction is going to give us the longest continuous carbon chain. So in this molecule here, we can say 1, 2, 3, 4. But that's not our longest continuous carbon chain. Our longest continuous carbon chain is 1, 2, 3, 4, 5. And so we call that the parent molecule or the parent molecule is the most common way we'll refer to it. Basically, you're gonna name everything else based on that. All right, so who remembers their organic numbers?
I remember that you'd be like 3
Don't even
something.
know what you're talking about.
So the way that we name these parent molecules, we have three different parent molecules up here, right? We have a longest continuous carbon chain of 3 versus 4 versus 5. The way that we name those is by organic nomenclature gets its own set of number-based prefixes. So when you first learn your inorganic nomenclature, we use the standard Greek numbers, right? Mono, di, tri, tetra, etc. The first 4 for organic are different.
I know what you're talking.
Yeah. Meth,
Meth, F, pro, but, pent,
then we're back to
like the normal ones.
the normal Greek based. Or those ones might be the Latin ones, but either way. Right, so our 3 different parent molecules here, we would name with different prefixes. And then we're just gonna stick ane on the end.
That's mean.
What? Trying it in a confusing way?
Yeah.
This is how we get practice.
You could start easier.
We did.
We didn't practice the other ones, you just told us.
We'll talk about the numbers here in a second. For this one, I just want you to count out what's the longest continuous carbon chain, and then I'll give you the number. We'll talk about the numbers.
I think it's 9.
So it's definitely not gonna be that way. So we go here. It's definitely not to the right. There's 1, 2, 3. If we go to the left, 2 more there, or 6, 7, 8, 9. So our longest continuous carbon chain in this case is 9. The prefix for 9, I have a table of the prefixes in a second, is gonna be known. So this would be a nonane.
But then when you add on the.
And then we take that, parent molecule, that parent chain, and we add prefixes. We had to modify it. So it's gonna be similar to other nonanes in that it has 9 continuous carbons, and that's the longest continuous carbons. Longest chain of continuous carbons. And then we're gonna say, okay, but it's not the same as all other nonanes. Because it has this group here and this group here and this here and this here.
So do you say known ane, or do you say known and then you add your other things in the middle and then you add ane?
So for hydrocarbons especially, I would write, you take your prefix and then you just put ane on the end. So propane, butane, pentane, hexane, heptane, octane, nonane.
Is that only for single bonds?
If, as soon as so this ane part here is telling us that it's an alkane, and our definition of an alkane was no pi bonds in all hydrocarbons. Only hydrocarbon. So if it's not an alkane, we're gonna change the suffix. So I'm gonna use the English terms, so make sure you can remember prefix versus suffix, right? Suffix goes at the end, prefix goes in the front. So by adding prefixes in front of our parent molecule, we modify it. Once you find your longest continuous carbon chain too, it can be helpful to circle it. Because that also makes it really obvious what are the other branches that are hanging off of it. What's different about the red branch versus the blue branch?
The red is 1, so it's meth, whereas the blue is 2, so it's F. Yeah.
Exactly. So all we're gonna use those same prefixes, those same numerical prefixes to name any branches as well, but we'll get there. As you mentioned, we haven't done much practice yet, so let's do the simple ones.
Okay.
So we already have that drawn on the whiteboard, but
Are we just doing the parent chain?
just so there's only one alkane, turns out, with the formula C3H8. So skeletal structure or the complete structure would look.
It's propane.
So it's propane. And no matter which way we twist it around,
Do you wanna use mine? You have to draw it the side of it.
so propane's sort of an easy one because there's really not that many ways we can twist it around. It's only 3 carbons. So but it doesn't matter which orientation it has, we're gonna get 3 carbons in a row. Which tells us our parent molecule is prop and it's an alkane, so we throw ane on the end. And when we get to C4H10, now we have to start being more careful because with 4 carbons, as we saw in the homework, there's more than one way you can arrange them. So here's what the ball and stick models would look like for C4H10.
So we'd be back.
One of them,
One of them.
they're 2 different molecules. You can't just twist one around to get the other without breaking a bond, right? That's what made them isomers instead of the same molecule. So if they're 2 different molecules, they have to have 2 different names. This is the #1 rule of nomenclature in organic chemistry, is the names have to be unambiguous. From the name, you've got to be able to get to just a single structure. Side note, how do we do the condensed structure for this one? If there's a branch, how do we do the condensed structure?
Oh, do you like draw a branch and you do the CH?
You can, although typically the whole point of the condensed structure is to try and draw it all and write it all in one line so that you could type it.
Would you type it above it?
Similar to what you just,
No.
so you do see that sometimes it's sort of a combined. So you would see it CH3, CH3, and then you'd see CH3 underneath.
Yeah.
You could just type it like that or even stick a bar character in between the 2. That's still not technically condensed structure. So what you'll see, and this is not something, we're not going to use condensed structure all that often, because we've moved past the ages of the printing press. But if you do see parentheses, it usually means it's attached to the parent molecule.
Oh.
Do you two know the keyboard shortcuts in Word or Google Docs for formatting? So there's some easy ones. Control I puts it in italics, Control B puts it in bold. Control U is underline. In Word, Control equals, we'll put it in a subscript.
Okay,
And Control Shift equals, we'll put it in a superscript,
which is above.
which is above. So you can actually type out your formulas for ions and stuff like that.
Doing that.
You can do it.
You can do it the long way, you go into
Right.
like special characters.
I was just writing them big.
That works too. It's a different keyboard shortcut in Google Docs that I don't remember off the top of my head. It's gonna be Control something, but it might be Control period and Control like the greater than and less than signs. But I would need to play around with it. But if you hover over the option, usually it'll tell you what the keyboard shortcut is. I'm a big fan of keyboard shortcuts because it saves you a lot of time.
I did it once on accident last year and I was like, how did I just do that? I need to remember
Which
this.
one how'd you say to do a big word? Control
In
what?
Word is Control equals and Control Shift equals. It's like Control plus. All right, so if the molecules have to have distinct names so that the names are unambiguous. The term ambiguous just means kind of poorly defined, or it could mean more than one thing. We use that a lot in Gen Chem when we talked about ambiguous numbers, right? In OChem, we want to make sure we don't have ambiguous names. And this is the lazy way of doing naming. And this comes from the petroleum industry. Basically, the way that they used to separate all these different molecules from each other, the way they still do in a petroleum refinery, is you basically have just one giant distillation tower. And that has sort of a temperature gradient going from top to bottom. So, and at the bottom, you feed in crude oil. And then it's very hot down here. And it cools down up here. And so we have this gradient, and then you have all these different, like, they call them ports. Where you basically, they're like buckets at different heights in this tower. And if they're all at different heights, they're at different temperatures. Which means you collect things that are condensing at different temperatures. Things that have different boiling points are gonna condense at different heights along this tower. And so they would just say, okay, well, anything that condenses at this height, we're gonna say it's hexanes, because it's a bunch of stuff that has 6 carbons. There's a lot of different ways that you can arrange 6 carbons, a lot of different constitutional isomers. So that's why they would just throw that S on the end. It's just a bunch of hexanes, a bunch of stuff with 6 carbons. It's gonna be methyl pentane mixed in with dimethyl butane, mixed in with regular hexane, mixed in with all of this other stuff. So we're trying to get away from that. That is a very ambiguous name. It can mean anything with 6 carbons. And so we're trying to go to the more unambiguous names. From an engineering standpoint, I will say that petroleum distillation, or petroleum refining is a really, really cool process. You'd be amazed at what you find that comes out of these different things. Road tar is just whatever is left over in the bottom. You feed crude in, everything else that is more useful evaporates and then recondenses and evaporates and recondenses. Whatever stays at the bottom is literally what they use, and they put a bunch of gravel in it, and that's what asphalt is.
Huh.
And then, you know, you've got octanes are gonna be down here, so that we use that for gas, but then all the other, like, there's a stage in between octanes and road tar that is basically Vaseline. Vaseline and aquifer and all those types of ointments are all higher melting points or higher boiling points than octane, but lower than road tar.
So road tar, like, does not break down in nature,
Not well. No,
but it can like get squishy on hot days.
it can, depending on how hot, and depends actually on where you got the road tar.
Oh.
Because different crude petroleum sources, if the crude petroleum came from Qatar versus coming from Venezuela, you're gonna have different impurities mixed in with it. And so you'll actually get different characteristics based on where you got the crude petroleum in the first place, and then how the refining process worked. Different refineries can be slightly different, different temperatures, which will affect things a little bit as well. I think I have a good figure. The next alkanes lecture involves some properties of alkanes. I think I have like a good flow chart of how this actually works in more detail. I'll make sure I throw that in there. Because it is a fascinating process. And the reason,
It's just from hot and cold.
basically, it's just a distillation. Just they have it set up so that you can do it continuously, instead of having to stop, add more stuff and distill it again. It is, that's chemical engineering. It's chemical engineers are the ones who figured out how to take that distillation process and scale it up and make it continuous so that you can put through thousands of gallons an hour. All right, so before we take our break, let's do this one. We've been kind of talking around it for a while now. If we have a branched alkane, we're still going to name the parent molecule the same way. So find your longest continuous carbon chain, use the right numerical prefix, put ane at the end, just like normal. And then we're going to modify it by putting another prefix in front of the parent molecule. So in this case, our branch is only a single carbon. So we're going to use that meth prefix, but we can't say methane pentane. We need something, instead of saying ane, we're going to change the suffix. So instead of ane, we're going to put YL. And YL as a prefix is basically saying it applies to whatever comes right after it. Trying to think of a good English example. I'm sure I'm blanking right now, but there's lots of words that immediately imply something comes right after it. I'm sure that there's I think the English term is a modifier. You will never see a methyl without, it's an adjective, so it has to have a noun after it. So you can say you have a methyl group, but it would be grammatically incorrect to just say you have a methyl.
You have a methyl.
That'd be like saying you have a green.
Yeah.
And people do that in slang, and I will say that, you have a methyl over here. I know I'm going to say that because it's really common, but it's not grammatically correct, because methyl, that YL as a suffix means it applies to whatever comes after it. And then here's where the numbers came in. If there's more than one place where you could put a methyl group, you have to specify. So in this case, there's more than one place we could put a methyl group. So we have to specify, in this case, the methyl group is on carbon 3. Versus you could put it on carbon 2. These two molecules are isomers of each other, but they're not the same molecule. Because to move a methyl group from carbon 2 to carbon 3, you would have to break a bond to do it. So even though they're both methyl pentanes, they're not the same molecule. What about this example down here, though?
To be on the board, but we want it to be on the lowest number.
So,
Right.
That would be on carbon 2 if we started counting from the other side. Or the other way you can think about it, if you took this molecule and you flipped it like a pancake, it's the same as this one. So if you always keep your numbers as low as possible, then that'll tell you, oh, if I count from over here, it's still 2-methylpentane. That's what I was talking about, how if you're not sure, name it. And if you get the same name 2 different ways, it's probably the same molecule. Or you messed up your naming, but we're gonna get really good at naming.
I remember really liking naming when we learned it in Gen Chem, and Atticus was like going crazy because it wasn't math, so he didn't get it. I was like, the tables have turned, this feels great for me now.
Yeah, you can't, and this last thought before we take our break. That is exactly why OChem gets a bad rap. It has a reputation of being a really hard class and being a weed out class because engineers and physics majors try to math their way through it, and you can't do that. And biologists, no offense to biologists, but biologists tend to try to memorize their way through classes that are unfamiliar. And you can't do that either. And so the two biggest coping mechanisms and the two biggest groups that have to take OChem tend to struggle with it because you have to think about things in 3 dimensions and you have to think about it in terms of electrons. You can't get away from the concepts and you can't memorize it. So it's not actually that hard if you're willing to engage it the way that you need to.
No, I really like it. Like, you just gotta know what to do and then you just do it.
Right.
But I guess that's how like people felt about Gen Chem math stuff, whereas I was like, this makes no sense.
Right. It's just a different skill set. And it really does. I don't think I've met a chemistry major that disliked OChem because chemistry majors either liked it initially or were able to change their mindset where they changed majors.
They're like, this isn't for me.
All right, let's take a break. Let's come back at quarter after
Sounds good.
and we'll do more practice.
Quarter after or
'Cause we're-
15?
Same.
Oh, okay. Because we only go to 50.
Yes, quarter after the hour, not quarter through that, yeah.
Some chow chow. What? You take this. Okay. What? You're just so silly. My head. Oh no, you're burning up.
No, feel my stomach actually.
You do feel hot.
What is this?
Maybe. Or you're just actually buying clothes that weren't in 2015 anymore. Yeah.
Alright. So when you're ready. Try redrawing these as their skeletal structure, because being able to see ball and stick and turn it into skeletal structure is its own sort of skill. It's good practice for visualizing these things. And then name them.
So sitting for class, I was also in this class. I just find there's no one else in here.
You've got room.
Could you still say 2-methyl?
It'd be a little redundant. Because on a propane, there's only one place to put a methyl. If you put it on either of the other carbons, you really just made butane. So when in doubt, it's better to be redundant than to be ambiguous. So if you're not sure, put the 2 there. If this was a 4-point question on a test, that's probably at least 3.5, if not 3 3/4. But if you needed the number and you didn't have it, it would be a bigger deduction. So when in doubt, put the number. I think typically that's what I do when I'm grading, if I'm remembering my rubric properly. is if you need a number and you don't put it, it's a half a point deduction, but if you don't need a number and you do put it, it's a quarter point. So it's like a sig fig error, basically. Because on this one, we definitely do need it. And just a note about I tend to use hyphens, dashes to differentiate between the prefixes and the parent molecule. Technically, that's not standard practice. Standard practice is to make this all one word. In true IUPAC, so it would be methyl propane. That starts looking a little bit harder to parse and more intimidating. So I tend to break it up by using this. Don't use a space though, because a space means something very specific when we get to ethyls or esters especially. So either run it all together as one word. You could even, I suppose, use an underscore, but that'd be even more non-standard. So stick with a dash or all as one word. The dash before the number is standard. So we have another pentane down here. It doesn't, I counted in kind of a non-standard way. Usually when you look at these, your default is to try and count left to right, because that's just how our brains have been trained to think in the US. Reading English and all that. However, if you count from any of the ends, you get 5. No matter where you start and where you end, you're gonna get 5. So I just picked one just to illustrate that it doesn't matter. Because no matter what, we're gonna get pentane.
And the 3.
And on the third position, there is what type of a group?
Methyl.
Ethyl. You need to specify that it's on the third carbon.
No, because you're always.
If it was a methyl group like up here, yes, because we can still get to 5 carbons as our longest carbon chain, regardless if it's on carbon 2 or 3. Technically, an ethyl on pentane, we don't need to say it's on carbon 3, because if we put an ethyl on carbon 2, that's not pentane anymore. If we put an ethyl on carbon 2, that's now hexane. Because now it's 6 is our longest continuous carbon chain. So that's definitely a case where it's a little bit tougher to see compared to methyl propane. So if you wanted to say 3-ethyl, if you weren't sure, put 3-ethyl pentane. All right, questions on these ones? What if we have multiple substituents? So anything that's attached to our parent molecule, we call a substituent. Constituent means makes up, so sub means it's a smaller part of something. So anytime we're talking about something added on to something else, it's a substituent. Now we actually do see a difference. It's the same molecule, it's still ethyl pentane, except we added one more substituent on there, and now it does matter which way we count a little bit. So if we have two choices that both give us pentane, we want to pick the one that has more branches or more substituents on it, because that's going to make it easier to name. Technically, there's another name that is unambiguous, would get us to the same structure, but the better habit that's going to serve you well as you get into the way, count in the way that has the most substituents attached. So in this case, we'd have three ethyl, two methyl pentane. This part, though, I'm not gonna worry about as much. Because it doesn't matter if I said two methyl, three ethyl. I'm still gonna draw the same structure. And different textbooks, when we start adding di, like if we had dimethyl, do you alphabetize that as D or M? Depends on which textbook you read.
Oh, really?
So I'm really not worried about the alphabetization. Maybe they've unified that a little bit since I first started teaching this class. When I first started teaching this class, I checked 3 different textbooks and got 3 different answers. So in that case, don't worry about it. As long as your name is unambiguous, don't worry about what order these are in. Matters where you put the numbers, but less so, did you say ethyl first or methyl first? So if we count the way that I have it numbered here, we get 3 ethyl, 2 methyl pentane. And just as an example, there are some molecules, this is the most correct name. We will see some examples of molecules where it's actually easier to count that way. That goes against what I just said about count the way that has the most substitutions. For some molecules, we're gonna have to do that. And then we get what's called a complicated, or what I call a complicated branch. And we'll get to naming those later. But this one does have 2 possible names, but this is the better name. Yeah. What's your longest continuous carbon chain for this one?
It's.
I got.
Wrong carbon. Yes, 6. So it's gonna, the parent molecule then is gonna be hexane. It's got 2 branches. They're both the same size. So it's gonna be dimethyl. And then we have to specify where the methyls are. Way we do that is if you say di anything, you've got to have two numbers in front of it. Unless it's a case where there's only one possible way to arrange things. But in general, there's two methyls here and here. We have to specify where both of them are. So it's gonna be 3,3-dimethyl. Right, it's tempting to just say 3-dimethyl. If you see di, you've got to have two numbers. Because the other thing you could have is you could have 2,3-dimethyl. The other temptation that we see is 1, 2, 3, 4, 5, 6. We had methyls on two different carbons. People get tempted to say 2-methyl, 3-methyl. Exactly. So anytime you've got the same prefix twice, or the same branch twice, you have to combine them.
But do we ever use mono?
We will a couple times, but not in terms of prefixes for naming. We'll use it more like, we'll talk about mono-substituted benzenes.
Okay.
Things like that, but we're not gonna, it's not gonna be monochlorobenzene, it would just be chlorobenzene.
But so then the rest of the like di-tri, then we go back to what we're already using. right?
Go back to the Greek prefixes, yeah. So that actually means that you could have a pentapentyl group.
Right.
Let's see if I can draw one.
I have a feeling I'm gonna mispronounce more things in this class.
That's okay. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4.
This is
5.
real?
2, 3, 4, 5. I'm sure somebody's tried to make it. This would be pentapentyl cyclohexane.
The dental cyclohexane.
So
But you'd have to say like.
then you'd have to,
1, 2, 3, 4, 5.
yes, because you could have 1, 1, 2, 2, 3 pentapentyl hexane.
Mhm.
Right? So if you see penta, you've got to have 5 numbers in front of it. That'd be a really extreme case.
Right.
Almost, in fact, I don't think I've ever asked a question that had a pentamethyl or anything like that ever before.
Okay. So the highest we'll typically go is tri.
You'll see tetra from time to time. We deal with tetrachloromethane. And just since I keep using it as an example, might as well explain this too. Anytime halogens also get their own prefixes.
Okay.
And the way that that works is because halogens typically are trying to form one bond, just like hydrogen. The formulas are gonna look like a saturated hydrocarbon, except you replaced a hydrogen with chlorine. So you could have,
Wait, sorry, say that last part again.
chlorine and all the halogens are gonna try and form one bond, right? Because they only have one vacancy. So what the formula generally looks like is you took your saturated hydrocarbon and replaced one of the hydrogens with a halogen. So instead of C3H8, you'd get C3H7Cl. Because the halogens in the formula and in the way we draw these are basically just replacing a hydrogen. So they're not part of your longest continuous carbon chain. very specific, longest continuous carbon chain, not longest continuous chain. And then we just stick chloro, bromo, fluoro, iodo in front. So, for instance, here, start with a simple one. 3 carbons is our longest continuous carbon chain. So it's going to be propane as our parent molecule. And then when I circled all 3 carbons, I had 2 things hanging out of the circle. So that tells us we got 2 branches. One is a methyl group and one is a fluorine group.
Does one take priority over the other? For like the numbering?
Yes. With halogens, it doesn't generally matter as much, but as basically as we keep adding more and more functional groups to our naming, whatever we've added most recently typically is the higher priority. There's a whole appendix at the back of the textbook
Okay.
that has like the list of priority. Halogens are more important than alkanes, and as soon as we add alkenes or other functional groups, those are going to be more important than the halogens. It's not super important with these, the halogens and the we'll call the alkyl groups. An alkyl group just means like an alkane branch. Alkyl groups and halogens are about the same priority. So but either way, in this case, we'd want to say 1, then 2, then 3. So we could say 1 fluoro, 2 methyl propane. Technically, the 2 is redundant on the methyl, but when we start getting these longer ones, it's a lot harder to see, and we'd rather be redundant than ambiguous. So our halogens are then going to be fluoro, chloro, bromo, iodo.
Do they need to be uppercase?
No, they do not need to be uppercase. And that actually brings up a good point with any of these named compounds. Any chemical period is not a proper noun. Unless it's like copyrighted pharmaceutical or something like that. So they only get capitalized if they're at the beginning of the sentence, just like any other noun.
Okay.
And I'm not sure what to do with the numbers in front, if that counts as being, I don't know if you would capitalize the F here, if the 1 comes before it, I think you would, but it doesn't really matter.
So like if we had a page on a test that just looked like this and you said name them and we wrote it all lowercase, that'd be fine.
Yes.
Okay.
If you're writing a lab report, like we'll deal with common names for molecules all the time. It's like eugenol is a molecule we're gonna work with a lot.
Did a guy named Eugene make it?
It's a good question. I actually don't know. That's the compound in clove oil. Clove oil is eugenol.
It's very soon.
Very soothing, topical anesthetic. Smells good.
Yeah.
Smells like Thanksgiving to me. Because of the, honey baked hams and all that.
Yeah.
Apple cider and cloves and apple cider is the way to go.
Oh, I've never tried
Hot
that.
apple cider. Guess actually you just get like treetop jug of apple juice.
Yeah.
And then you just take an orange and you stick a bunch of cloves into the skin of the orange and you just heat it on the stove with the orange and the cloves in there, and it tastes and smells really good. And it smells like you spent a lot of money on like getting fancy apple
Yeah,
cider
yeah.
from Apple Hill or something. Anyway, you would only capitalize, despite the fact it might be named for Eugene, you're not gonna capitalize it unless it's at the beginning of a sentence. But again, I'm not gonna mark you down on that, that's just best practices. All right. The last 5 minutes,
Kind of a weird question,
okay?
but all of the chemicals that we smell, do they have to have a benzene ring to have a scent to them?
No. So the term aromatic is a misnomer. It's not accurate.
Okay.
Aromatic, meaning fragrant, does not mean aromatic chemically. And we'll get into why that is later.
Okay.
But lemon oil, we'll do a lab that has lemon oil, same lab where we deal with eugenol. Lemon oil is aromatic, it's very fragrant, but it does not have a benzene ring or anything that's classified as aromatic in the
Okay.
structure. So that's just a holdover from when they first discovered these things. All right, last. Last thing we're gonna talk about is complicated branches. And we're gonna spend, I think I have a whole section on this in the next lecture as well, but just so you've seen it once now. A complicated branch is when your branch has a branch. And so, for instance, what's your longest continuous carbon chain here? 7. We can't start counting here and count the way that gives us the most substituted. Because then that's not 7 in a row, it's only 6, right?
Yeah.
So it's a heptane. And this whole thing is hanging off. Did Carl teach you how to name that group at all? Didn't get it, oh, perfect, then we're starting from scratch, that's ideal. Because I don't like having to unteach the common name for this. So when you have a branch within a branch, you're gonna use a prefix on your prefix.
Okay.
So
So like methyl ethyl?
exactly, that's
Okay.
exactly what it is. Your longest chain coming off of the parent molecule is an ethyl. But then your ethyl has a methyl attached to it. That doesn't seem too bad. Except we need to differentiate, is the methyl attached to the ethyl or is the methyl attached to the heptane?
The methyl is attached to the ethyl, but the ethyl is on the heptane.
Right. So mathematically, if we were gonna say. If I wanted to add the 3 plus 2 before I multiplied, how would I do it? Parentheses. That says the 3 gets added to the 2 and then you multiply the whole thing, right? We're gonna use the exact same thing here. We're gonna use parentheses. If you put the parentheses around the whole thing, that's telling the reader the methyl is applied to the ethyl. And then the whole thing is attached to the heptane.
And you say 4 methyl ethyl heptane?
Bingo. So that means that no matter how complicated your branch is or how big your secondary branch is, you can always use your same approach. You just use the parentheses to say, and you can even use nested parentheses if you needed to. If you had a chlorine attached to the methyl, attached to the ethyl, you could do that.
Right.
Again, we're starting to get into the like, that would be absurd territory.
Yes.
But we can do that.
Okay.
if we're careful about how we apply our rules. All right, one more example with this. Sorry, I have to make the parent molecule long enough that you have to use the parentheses.
Oh,
2, 3, 4, 5, 6, 7, 8, 9. So it's no name. And your longest continuous carbon chain that starts attached to the parent molecule,
is it 3 or 4?
3.
Oh.
So if you counted the one that was already part of the parent molecule, you'd be
Yeah.
double counting, right? So that makes it a propyl group. But then your propyl group has a methyl attached. Could you have a propyl group with a methyl attached in 2 different places? So we need to specify where the methyl is on the propyl.
1.
1. That's carbon 1 because it's the one that's directly attached to the parent molecule. So 1 methyl propyl, no name. Then do we need another number?
Yeah, the 5, because it's the parenthesis group is coming off of the.
Bingo. We have to also specify that it's on carbon 5 of the no name. So 5 parentheses 1 methyl propyl end parentheses no name. Doesn't exactly roll off the tongue, but once it's written and you know these rules, you should always be able to get back to the right structure.
Is the dash between the methyl and the propyl necessary?
No,
Okay,
so, but don't put a space.
right.
In fact, I tend to do that too. When I'm writing these complicated branches, a lot of times I will not put a dash there, but I will put a dash there. I don't know why, it just doesn't look as bad when you do it that way to me. But either way, I'm gonna try to be as consistent as I can using the dashes so that y'all can read my chicken scratch. But I think the way that it would normally be written would be 5, 1 methyl propyl no name. And that just does not look pleasant to me, especially when it's all the same color. Or typed, it just starts looking like a wall of text. And
Right.
so I like to break it up this way by color or with the dashes.
Okay.
All right. It's a good start there. We'll get lots of practice with that at the beginning of class on Thursday. And we'll add cyclo groups and we'll start doing more stuff with chlorines and all that good stuff as well.
See you in lab.
See you in lab, go get some food. You already had some snacks, but,
I gotta go to student senate and get
oh, good.
appointed today.
I'm also getting appointed, but
She has to run science club, cause she's my vice pres, so one of us has to be there.